What is space-time?
You already know.
What part of the timeline of the universe is the James Webb Telescope serving?
We are mapping right now with the James Webb Telescope.
The one thing scientists and astronomers have feared most is being confirmed by the James Webb Telescope, and we might have to throw everything we know about our universe's inception out the window. The theory about how our universe came to be has been one hot topic between scientists, physicists, and astronomers, but a recent JWST discovery has just proved it all wrong. This discovery has to deal with the existence of time in our universe, and nobody was prepared for the shock dished out by the JWST. What did this powerful telescope discover about time and its existence? Did the JWST really prove that time does not exist? Join us as we explore how the James Webb Telescope shocked the entire space industry by proving that time doesn't exist. The Big Bang Theory, which notes that our universe has been expanding since it began over 14 billion years ago in a hot and dense state, has been disrupted by some recent images from the new James Webb Space Telescope. Any layman who sees these awe-inspiring images would plainly admire them, but it was a different case for the most expert of cosmologists and astronomers. Although the pictures surprised them as well, the cause of their surprise was for a different reason. When this image from the JWST was analyzed, several technical astronomical papers were published online. The authors of these papers reported largely that the photos show several galaxies, some of which were surprisingly small, smooth, and shockingly old. In addition, there were several surprises, not all were pleasant. In fact, one paper's title began with the candid exclamation, "Panic." The reason why these images from the JWST caused panic among experts was that the photos consistently contradicted the Big Bang Theory. And since that hypothesis has been defended for decades as the truth by several scientists, the new data is causing turmoil among these experts. Because if the Big Bang Theory, which has been widely accepted for decades, suddenly becomes wrong, where will the entire world of science start? What else could be contradicted? And the number of astronomers bothered about this recent development is alarming. One is Alison Kirkpatrick, an astronomer at the University of Kansas in Lawrence. She said, "Right now I find myself lying awake at 3 in the morning and wondering if everything I've done is wrong." And it's not too complex to explain why these too smooth, too old, too small, and too numerous galaxies are incompatible with the Big Bang Theory. In an expanding space, galaxies and other objects are not supposed to appear smaller as the distance increases. Instead, after a particular point, they appear bigger because their light is meant to leave them when they're nearer to us. This is in sharp contrast to non-expanding ordinary space, where objects appear tiny compared to their distance. But in the JWST's case, the images showed objects that grew tinier by the distance. Even galaxies with more mass and brightness than our own Milky Way galaxy looked 2 to 3 times smaller in JWST's image than in other images taken by the Hubble Space Telescope. Also, the new galaxies appeared to have redshifts that were also 2 to 3 times greater. These listed facts are not associated with an expanding universe, contradicting everything. But from the Big Bang's view, expanding universe hypothesis, these distant galaxies must be tiny to compensate for the theorized optical illusion, implausibly small. One galaxy in space called the GHZ2 was observed as well. Usually, it is always brighter than our Milky Way, but when it was analyzed, it was seen to be only 300 light-years in radius. This is 150 times smaller than the Milky Way's radius. Even its surface brightness would be 600 times more than that of the brightest galaxy in the local universe. The galaxy's density and even those of other galaxies in the new images presented by the JWST would be tens of thousands of times that of present-day galaxies. Tiny and smooth galaxies signify that there is no expansion, and in a nutshell, that means there was no Big Bang. Scientists supporting the Big Bang Theory have known right from the images sent by the Hubble Space Telescope that their assumptions require the existence of these tiny, ultra-dense, Mighty Mouse galaxies. Now the James Webb Telescope has made things worse. The same theorists have proposed that the tiny galaxies grow into present-day galaxies by colliding to become more spread out. An analogy to this hypothetical collision process would be picturing a centimeter-long magical toy car that weighs as much as an SUV and grows into a real SUV by colliding with many other toy cars. However, to the dismay of the Big Bang theorists, the JWST discovery also shot through this far-out scenario. If you could believe the toy car story, you would at least prepare for some fender dents in the colliding cars. Big Bang theorists looked forward to seeing badly mangled galaxies, but the JWST only showed neat spiral forms and very smooth disks, as we see in today's galaxies. So basically, the data ultimately destroyed the merger theory. With few or no mergers, there is no way tiny galaxies could become 100 times larger. Therefore, they were not small to begin with, and as a result, the optical illusion from the expanding universe theory is untrue. As there's no illusion, it means there is no expansion, because the illusion is a predestined prediction from expansion. Thus, this has resulted in panic among Big Bang supporters. Tiny and smooth galaxies mean no expansion, meaning there was no Big Bang. And also, too old and too many galaxies mean the same thing. The James Webb Telescope uses several filters to take its images in the infrared part of the spectrum. Thus, the colors of distant galaxies can be seen. This enables astronomers and scientists to estimate the age of the stars in these galaxies, because young hot stars are blue and older, cooler stars like our Sun are yellow or red. According to the Big Bang Theory, most far-off galaxies in the JWST images are seen as they were only 400 to 500 million years after our universe's inception. Yet already some of these galaxies have shown stellar populations that are over 1 billion years old. Since nothing could have originated before the Big Bang, the existence of these galaxies demonstrates that the Big Bang did not happen. And just as there must be no galaxies older than the Big Bang if the Big Bang theories were valid, theorists expected that as the James Webb Telescope peered deep in space and back in time, there would be fewer galaxies and, in the end, no dark age in the cosmos. But another paper demonstrated that galaxies as big as the Milky Way were common even a few 100 million years after the theorized Big Bang. Furthermore, the authors noted that the new images show at least 100,000 times as many galaxies as theorists predicted at redshifts of more than 10. There is no way that so many large galaxies could have formed in such little time, so again, no Big Bang. And all this just explains that time really does not exist. According to one theory, it is nothing but a human construct to help us determine between now and the perception of our past. The concept of time is basically an illusion consisting of human memories, everything that has ever been and will be happening right now. According to a group of esteemed scientists who aim to solve one of the universe's mysteries, that is the theory. Many people don't ponder the concept of time, but there is nothing in the laws of physics to state that it should move in the forward direction that we know. The laws of physics are proportional, which means time could have easily moved in a backward direction as it does forward. In fact, some adherents to the Big Crunch theory have once stated that when the universe stops expanding and starts contracting back in on itself, time will also run backward. And also, as the universe grows smaller, it will get hotter. One way to think of this is as the opposite of the Big Bang. Instead of cooling and expanding, the universe will heat up and shrink. Eventually, everything in the universe will collapse into a tiny point right where it began. But then what? Well, if you're asking yourself this question, you're not alone. People have always thought about the next thing that would happen after a big crunch occurs. For example, some people believe the universe may start afresh with a Big Bang, while others have theorized that the universe will blow up like a bubble in a new place. Some even believe this process happens multiple times, resulting in many other universes. And this dilemma of our interpretation of time moving in a forward motion has caused scientists to question why. Ultimately, some have concluded that time is just a human construct. They say there is a block universe where space and time are connected, also known as space-time. The theory, backed up by Albert Einstein's theory of relativity, notes that time and space are part of a four-dimensional structure where every event that has taken place has its own coordinates in space-time. This would enable everything to be real, meaning that the past and even the future are still present in space-time, making everything as important as the present. Massachusetts Institute of Technology physicist Mark Tegmark once addressed this in a statement. He said, "We can portray our reality as either a three-dimensional place where stuff happens over time or as a four-dimensional place where nothing happens. If it really is the second picture, then change is an illusion because nothing changes. It's all there, past, present, and future. At any given moment, we have the illusion that the past has already happened and the future doesn't yet exist, and things are changing." Julian Barber, a British physicist who has written multiple books about time, also has his perspective as he talks about everything as a series of nows. He said, "All I'm ever aware of is my brain state. I only feel like I have a past because my brain contains memories." Dr. Barber told a physicist and author named Adam Frank in the book About Time, Cosmology and Culture at the Twilight of the Big Bang, "As we live, we seem to move through a succession of nows, and the question is, what are they?" He explains, adding to the space-time theory where everything has its own place, you can imagine it as a country or landscape. Each point in this country is a now, and I call the country Platonia because it's created by perfect mathematical rules, making it timeless. He also added that what we believe as the past is an illusion formed in our brains. This brings us back to Albert Einstein and the theory he noted about space-time. This theory has caused some confusion in physics, and scientists are now pondering what if Einstein was wrong. Would killing off space-time theory help us better understand the universe? That would be a lot. But just as it is in history, revolutions are the lifeblood of science. Bubbling undercurrents of disquiet boil over until a new regime emerges to seize power. Then everyone's focus turns to overthrow their new ruler. The king is dead, long live the king. This has happened many times in the history of astronomy and physics. Initially, we believed Earth was at the solar system's center. This idea stood for over 1,000 years until Nicholas Copernicus theorized that the whole system would be a lot easier if we were just another planet orbiting the sun. Then, despite much initial opposition, the old geocentric picture finally buckled under the weight of proof from the newly invented telescope. And Isaac Newton also came up with his theory, saying that gravity makes planets orbit the sun. He noted that all objects with mass have a gravitational attraction around each other. So according to his views, we orbit the sun because it's pulling on us, and the moon surrounds Earth because we're drawing on it. Newton's theory dominated for almost 3 centuries before Albert Einstein turned up in 1915 to overthrow him with his general theory of relativity. This new picture neatly explained inconsistencies in Mercury's orbit and was famously confirmed by observations of a solar eclipse off the coast of Africa in 1919. Instead of a pull, Einstein saw gravity as the result of curved space. He theorized that all objects in the universe sit in a smooth, 4-dimensional fabric called space-time. Huge objects like the sun curve the space-time around them, so Earth's orbit is simply the result of our planet following this curvature. To us, that appears like a Newtonian gravitational pull, and Albert Einstein's space-time theory has been on the throne for over 100 years, diminishing all pretenders to its crown. The discovery of gravitational waves in 2015 was a decisive victory, but like its predecessors, it too might be toppled over soon, and that is because it is incompatible with the other big beast in the zoo of physics, quantum theory. The quantum world is infamously bizarre. Single particles can be in 2 places at once, for example. In the 1930s, Erwin Schrödinger devised a famous way to show how awkward this idea is. He pictured a cat in a sealed box and a vial of poison attached to a hammer. The hammer is hooked to a device that observes a particle's quantum state. Whether or not the hammer smashes the vial and kills the cat hinges on that measurement. Quantum physics notes that until such a measurement is made, the particle is simultaneously in both states. This means the vial is unbroken and broken, while the cat is alive and dead. However, such a picture cannot be reconciled with a continuous, smooth space-time fabric. Even Sabine Hossenfelder, a theoretical physicist at the Frankfurt Institute for Advanced Studies, said, "A gravitational field cannot be in 2 places at once." According to Einstein, space-time is warped by matter and energy. Still, quantum physics says matter and energy exist in multiple states simultaneously. They can be both here and over there. So where is the gravitational field? asks Hossenfelder. Nobody has an answer to that question. It's kind of embarrassing, she said. And if you try and use general relativity and quantum theory together, it doesn't work. Above a certain energy, you get larger probabilities than 1, said Hossenfelder. 1 is the highest probability possible. It means an outcome is inevitable. And equally, calculations sometimes give you the answer infinity, which has no real physical meaning. The two theories are therefore mathematically inconsistent. And so, like many monarchs throughout history, physicists are seeking a marriage between rival factions to secure peace. They're searching for a theory of quantum gravity, the ultimate diplomatic exercise in getting these two rivals to share the throne. And this has seen some theorists turn to some outlandish possibilities. Arguably the most famous is string theory. It's the idea that subatomic particles such as electrons and quarks are made from tiny vibrating strings. Just as you can play strings on a musical instrument to create different notes, string theorists argue that different combinations of strings create other particles. The attraction of this theory is that it can reconcile general relativity and quantum physics, at least on paper. However, to pull that particular rabbit out of the hat, the strings must vibrate across 11 dimensions, 7 more than the 4 in Einstein's space-time fabric. As yet, there is no experimental evidence that these extra dimensions really exist. It might be interesting mathematics, but whether it describes the space-time in which we live, we don't really know until there is an experiment, said Jorma Luco of the University of Nottingham. And partly inspired by string theory's perceived failings, other physicists have turned to an alternative called loop quantum gravity, LQG. With this, they can get the two theories to play nicely if they do away with one of the central tenets of general relativity, that space-time is a smooth, continuous fabric. Instead, they argue that space-time comprises a series of interwoven loops, that it has structure at the smallest scale. This is a bit like a length of cloth. At first glance, it looks like one smooth fabric. Look closely, however, and you'll see it is made of a network of stitches. Or alternatively, think of it like a photograph on a computer screen. Zoom in and you'll see that it's made of individual pixels. The trouble is that when LQG physicists say small, they mean small. These defects in space-time would only be apparent on the level of the Planck scale, around a trillionth of a trillionth of a trillionth of a meter. That's so tiny that there would be more loops in a cubic centimeter of space than cubic centimeters in the entire observable universe. If space-time only differs on the Planck scale, then this would be difficult to test in any particle accelerator, says Luco. You'd need a 1,000 trillion times more powerful atom smasher than the Large Hadron Collider LHC at CERN, one about as big as our entire Milky Way galaxy. However, a team of physicists from the UK, France, and Hong Kong may soon have another way to test this idea. They hope to use an ultra-cold gas of several billion cesium atoms existing in a state known as a Bose-Einstein condensate to see if gravity is really quantum after all. In the meantime, though, the universe itself provides another way to look for tiny space-time defects. Light arriving here from the furthest reaches of the universe has traveled through billions of light-years of space-time along the way. While the effect of each space-time defect would be tiny, interactions with multiple defects might add up to a potentially observable effect over those distances. Astronomers have used light from far-off gamma-ray bursts for the last decade to look for evidence supporting LQG. These cosmic flashes result from massive stars collapsing at the ends of their lives, and there is something about these distant detonations we currently cannot explain. Their spectrum has a systematic distortion to it, said Hossenfelder, but no one knows if that happens on the way here or if it's something to do with the source of the bursts themselves. The jury is still out. To make progress, we might have to go a step further than saying space-time isn't the smooth, continuous fabric Einstein suggested. According to Einstein, space-time is like a stage that remains in place where the actors are treading its boards. Even if no stars or planets were dancing around, space-time would still be there. However, physicists Lauren Friedel, Robert Lee, and Georgia Minnick think this picture holds us back. They believe space-time doesn't exist independently of the objects in it. Instead, space-time is defined by the way objects interact. That would make space-time an artifact of the quantum world itself, not something to be combined with it. It may sound kooky, said Minnick, but it is a very precise way of approaching the problem. The attraction of this modular space-time theory is that it might help solve another long-standing problem in theoretical physics regarding something called locality and a notorious phenomenon in quantum physics called entanglement. Physicists can set up a situation whereby they bring two particles together and link their quantum properties. They can then separate them by a large distance and find that they are still linked. Change the properties of one and the other will change instantly, as if the information has traveled from one to the other faster than the speed of light, in direct violation of relativity. Einstein was so perturbed by this phenomenon that he called it spooky action at a distance. Modular space-time theory can accommodate such behavior by redefining what separating means. If space-time emerges from the quantum world, then being closer in a quantum sense is more fundamental than being close physically. Different observers would have different notions of locality, said Minnick. It depends on the context. It's a bit like our relationship with other people. We can feel closer to a loved one far away than the stranger who lives down the street. You can have these non-local connections as long as they are fairly small, said Hossenfelder. Friedel, Lee and Minnick have been working on their idea for the last 5 years, and they believe they are slowly making progress. We want to be conservative and take things step by step, said Minnick, but it is tantalizing and exciting. It's a novel approach that looks to gravitational the quantum world rather than quantizing gravity as in LQG. Yet, as with any scientific theory, it needs to be tested. And so the trio are currently working on fitting time into their model. Now, this might sound very esoteric, something only academics should care about, but it could profoundly affect our everyday lives. We sit in space, we travel through time, and if something changes in our understanding of space-time, this will impact not only our understanding of gravity, but quantum theory in general, said Hossenfelder. All our present devices only work because of quantum theory. So if we understand the quantum structure of space-time better, this will impact future technologies, maybe not in 50 or 100 years, but maybe in 200, she said. The current monarch is getting long in the tooth and a new pretender is overdue, but we can't yet decide which of the many options is the most likely to succeed. When we do, the resulting revolution could bear fruit for theoretical physics. So what should astronomers, scientists, and physicists do about this situation? Let us know what you think in the comments section below.